Good afternoon. My name's Fergus Tate and I'm the Lead Safety Advisor for Roads and Roadsides here at the New Zealand Transport Agency. In my presentation today I want to talk to you about how we at the New Zealand Transport Agency are working with our partners at the Safe Road Alliance to use iRAP to help identify road safety issues and to develop solutions. So in the presentation I'm going to briefly discuss the Road Safety Alliance. I'm going to discuss, give you a quick background on iRAP, and then I'm going to look at how we use iRAP to identify improvement locations and select treatment options and assess crash reduction benefits. The Safe Roads Alliance is a professional services alliance that has been employed to identify safety improvements and develop solutions and take these solutions through to procurement. They do not actually procure the work themselves. So they're in the front end of the professional services. It's effectively an extension of our own NZTA workforce, and it's looking at two programs. The first program is based around the Safer Journeys Roads and Roadsides business case. This looks at 66 high-risk corridors in the country. Those are corridors that have a high collective risk, and they cover 23% of the network, on which 44% of the deaths and serious injuries occur. These are corridors with medium, high and high iRAP scores. The second program is called the Gap Analysis, and this covers all of those roads which are not covered by the Roads and Roadsides program or by other programs such as our Capital Improvements program or our Minor Safety Works program. The Gap Analysis tends to focus on low-cost solutions such as curve signage and lining, delineation, the use of audio-tactile profiled markings, and low-cost measures that are spread thinly across the network. The other thing about Safe Roads is that they actually have a number of key performance measures which are associated with their success. The first is that they have a target to reduce deaths and serious injuries by over 1,400 over the next 10 years. Improving the iRAP star rating on 424 kilometres of the 66 corridors from a star rating of 2 to a star rating of 3, and increasing the iRAP star rating to above 3.5 for a further 135 kilometres. And I know 3.5 sounds like a strange number, and I'll talk to you a little bit more about why we chose 3.5 stars a bit later in this presentation. iRAP, like other RAP programs, has three protocols: risk mapping of both personal and collective risk, star ratings and monitoring. Because iRAP star ratings were developed in around about 2009-2010, they precede the current iRAP V3 model, which has about 63 variables. So it's a much coarser tool than the iRAP V3 model that many of you will be associated with. But the 18 variables which I've listed here align to three different crash road protection score models. So they cover the runoff road protection score, the head-on road protection score, and the intersection road protection score. And together, those three crash types make up 85% of the crashes that occur on New Zealand's highways. One of the things about the RAP program, or one of the important things about star ratings, is that they cover such a wide range. At one extreme we have 5-star roads on which everything is perfect or extremely good, and at the other extreme we have 1-star roads on which everything is rubbish effectively. But in between these it's possible to trade different variables against each other. So for instance, if we have a 2-star road that is heavily governed by a winding alignment, rather than addressing the alignment, it's possible to compensate and increase the star rating by, for instance, increasing the sealed shoulder width on that alignment to give drivers a greater recovery area, and by managing the roadside hazards so that if a vehicle does lose control, its occupants are less likely to be seriously injured or killed because they're not striking trees or poles or other roadside hazards. So it's important to understand that we don't necessarily have to address the thing that's driving a poor iRAP score. We can use other tools in the toolbox to help minimise the impact. Now I'd just like to look at how we are using the iRAP to identify improvement locations, select treatment options, and assess the crash risk benefits. The first thing that we need to consider is what is the treatment philosophy that we're trying, or what it is that we're trying to achieve. As the majority of corridors under the Safer Journeys Roads and Roadsides program have high and medium-high collective risk, we're generally looking at safer corridor type treatments or safe system transformations. These are the ones in the upper right corner of the diagram. The types of project that will be involved in these sort of situations is managing roadside hazards, as I've mentioned before, looking at increasing shoulder widths, as well as centerline treatments and barrier treatments, both on the side and down the central median of the highways, and transformation of intersections with large diameter roundabouts or other innovative solutions. At the other end of the spectrum, the gap analysis type work that we've talked about are focused on safety management and include treatments such as signage, delineation and speed management. These lower cost measures don't really lend themselves to analysis using iRAP, so I'm going to focus in the rest of this presentation on our National Roads and Roadsides program and how we use the tools in that situation. So having identified what it is that we want to achieve for a corridor, we can use tools such as our iRAP analysis tool or spreadsheets to identify which sections of the highway we want to look at inside those corridors. And we can actually ask in this iRAP analysis tool, for instance, to identify all sections with winding alignments that have narrow shoulders and lots of roadside hazards. And we can plot this data and then plot the road protection score across the network, either through the CAT tool or through our spreadsheets, and we can look at where we've got spikes. Now we've got a number of major spikes that go down to 1 star in the figure here, and what they're showing is typically the major intersections on this route, and that's why they're 1 star. So across the bottom in the orangey brown section, we've got the 3-star highway road protection scores, and you can see that we're approaching 2-star in a number of other locations other than those key intersections, and we can actually go down a level and look, for instance, at the road protection score for runoff road crashes on the left-hand side of the highway. And this is identifying where we've got sections where we need to have hazard management, or we dig deeper into the picture to understand what's going on. So we would be focusing on these low 3-star and potentially 2-star sections where the left-hand side road protection score is indicating we've got a problem for either a high likelihood of runoff road or a high severity of outcome. So one of the things that we can do, as I've said previously, is we can increase the shoulder width. And this figure here looks at the relationship between crash risk and the width of the shoulder on the highway. And what we find is that if we are able to increase the shoulder width from, say, 0 shoulder width out to 1 metre, we can reduce the likelihood of a crash by 36%. So putting a shoulder width on, even though the alignment may be tortuous or winding, we can actually pull the crash risk down substantially using this type of, by putting in shoulder width. And you don't even have to do it at the over the whole length. What you can do is be selective, and it may be just increase the shoulder width on the outside of bends, which is where you're going to need it the most. So shoulder widths help us to reduce the likelihood of crashes. The other thing is roadside hazard management, which is all about reducing the consequences of a crash should one occur. And typically we're looking to use barriers as opposed to clear zones. We prefer barriers because what we were finding is that 30% of our vehicles were striking objects beyond a 9-metre clear zone. And so we would have to have much wider clear zones than what's often accepted as the standard of 9 metres. And what we then start to find is as those clear zone widths get bigger and bigger, the likelihood of rollover crashes increases as well. So what we've tended to do is use roadside barriers because these are energy absorbing, and what we find is that for roughly 30% of the injury crashes that impact a roadside barrier end in a death or serious injury, which is significantly lower than the 70 or 80% of death and serious injury should the vehicle strike a large tree or a culvert or some structure. So that's why we're fancying barrier systems in our roadside hazard management for run-off road crashes. In terms of head-on crashes, we've got a number of things we've been looking at. One of those is this wide centreline trial, where we're putting in double centre lines separated by typically 1.2 to 1.5 metres. And what we've been finding is with these wide centre lines, we get about a 20% reduction in injury crashes at locations, the 15 locations that we've been monitoring. We also get a 30% reduction in fatal and serious injury crashes. But probably more importantly, because the crash that these features are supposed to address is the head-on crash, and those head-on crashes typically result in multiple deaths and injuries, at those sites that we've treated with a wide centre line, we've had a 50% reduction in the deaths and serious injuries that occur at those sites. So they've been very successful and a part of our iRAP toolbox. The other, of course, is median barriers. And one of the things that we've been experimenting with is narrow medians with median barriers. This is actually an older example from Rangariri, but typically once volumes get up above 10,000 vehicles a day, we would start to retrofit the wide centre lines with a median barrier because of the high likelihood of head-on crashes. And in this case, looking at this location here, we've actually had 100% reduction in head-on crashes at the treated locations, not surprisingly, and a 65% reduction in death and serious injuries overall. So these median barriers are extremely effective in reducing death and serious injury and have a major impact on lowering the head-on RPS risk scores. In terms of intersections, which is the third RPS model that we've been looking at, we've been looking at channelization, or the use of left in, left out intersections where there's no cross-turning movement, such as the one shown in the figure here, which reduces, and these work well where we've got central median barriers, because obviously you can't make the right turns, and they've been extremely successful. And one thing that we've been working on more recently is our rural intersection active warning system. This system lowers the speed limit on the main road when there is a vehicle present on the side road. So if you look in the lower figure, you can see that there's a vehicle that's looking to pull out onto the white station wagon behind the motorbike that's looking to pull out onto the road. And as a result that vehicle's been detected, the speed limit of the main line has been dropped. This has been very effective, and it aims to reduce the impact speed should a crash occur. And at the sites that we've treated so far, we've had more than a 70% reduction in deaths and serious injuries at treated sites. So we're implementing a lot more of these rural intersection warning systems. Finally, we've been doing some transformation work, and in this case we've been converting a T-junction. This is near Waitomo, a tourist area where we had a lot of difficulties with the T-junction, and we've converted it to a large rural roundabout with a significant reduction in deaths and serious injuries. So that's how we can use iRAP to identify what the issues are and what sort of treatments from our toolbox we're likely to want to apply. And once we've done that, we can plot the road protection score. You can see underneath the black, which was the original score, and in this case we've looked at two different options to improve the highway, a purple one and a blue one. They're a bit hard to see, I realise, and they show how the KiwiRAP score will alter when we put these features in on the road, and then we can use that to calculate the saving in injury crashes that result. Because we have a strong relationship between the KiwiRAP score and the injury crash rate, we can actually say if we had a 2.5 star road initially, we had around about a 34 crashes per 100 million vehicle kilometres on that section of highway, so we can calculate the number of crashes we had in the before case, or we can measure them there. And then we can say, if we take this to a 3.5 star road, that will drop to around 18. So it's a significant reduction. It's nearly a 50% reduction from going from a 2-star or 2.5 star road to a 3.5 star road. And I said to you earlier, our aim is to raise a number of highway sections to 3.5 star. That's because that's the point where the relationship starts to bottom out and tail out. And in fact, we don't even look at 5-star roads, because what we're finding is 4-star gives us almost the same benefit as 5-star, as you can see on the graph, but it's a much less cost. So our target is 4-star, but if we can get the bulk of our rural roads up to 3.5 star, we will have significant crash reductions. Thank you, and if you want to send me an email or get in contact about anything you've seen, my details are here. Thank you very much, and good luck for the rest of the conference.